Hey, I'm Dr. Patton, and I'm going to talk to you about measures of central tendency and how to compute those in Excel. Those are two separate videos, though. Okay, let's see. There we go. So basically what we're going to be going through is different ways to describe the center of a distribution. So we'll learn how to compute the mean, median, and mode. So central tendency is a statistical measure that describes the center point of a distribution of any data set. And this, just to remind you what a distribution is, this is a normal distribution. Not every distribution is normal. Many of them are, and most of our statistical tests are based around normal distributions, but not every distribution is normal. But we want to know the center of this distribution, which would be roughly, right here, the center of this distribution. So we want to know how far apart two distributions are, how close they are, so we can say either they're different or they're not different. And of course, spread has something to do with us being able to say that those distributions are different or not. That's variance. That's a different lecture that we'll talk about after this one. So, but for right now, we're going to focus on the center of the distribution. The first thing we need to know is where is it located before we can talk about how much of a spread it has. Again, those measures of central tendency that we're going to talk about are mean, median, and mode. Three totally different concepts that are computed in different ways. So the mean is just the average, right? It's your typical average. Like we always say, average those two numbers together. Same thing. That's the mean. The median is a little bit different. It's the middle value. So you're going to look at the numbers in sequence and look for the middle value in that case. And the mode is just the most frequently repeated value. So let's take a look at some of these. My dots appear at the inappropriate time. Oh well, that's fine. So we've got these values here, 12, 17, 18, 17 again, and 13. If we want to take the mean, what we would do is add them all together, which is 77, and divide by how many there are, which is 5. We end up with 15.4 is the mean. If you want to look at the middle value, again, you put them in order, and you look for the middle, the value that's in the middle. And in this case, the median is 17. And when we're looking for the mode, we're looking for the number that occurs most often, which again is 17. Just count them up, right? Everything occurs once except for 17, which occurs twice. So the mean is 15.4, the median is 17, the mode is 17. These are all pretty close together. This is a pretty normal distribution. In a normal distribution, the mean and the median are the same, or approximately the same. This is what that looks like if you were to graph it out, what we just computed there. So green is the mean. It's a little bit lower than the median and the mode, and they're in exactly the same place. So this is just a graph of what you're seeing, and you can infer that it's a fairly normally shaped distribution. There's not nearly enough data points to actually get a good representation of what's actually going on here, but it's easy to compute, so that's why there's only 5 numbers. Okay, so this is a frequency histogram that you're seeing here, so it's graphing how many times each number shows up. So it's easy to tell where the mode is on this one. It's the highest. It's the highest bar. Okay, so you're going to be writing these things out for homeworks, for exams. You're going to be reading these things. So it's good to know how you're actually writing these things out, how you should be writing them out, and not to be confused when you see them in the literature. For the mean, and remember the mean is the most common measure of central tendency that we're going to have. The mean is different when we're talking about a sample versus a population. And so is the number of members of a sample population. So when we're talking about the number of people in a group, and it's a sample, it's a little n. And if we're talking about the number of people in a group and it's the whole population, it's a capital N. this is how you know whether you're looking at a sample or a population. Big N, little n. Cool. For mean, this is going to change with sample and population as well. So for a mean, you're looking at x bar. It's a lowercase x bar. We call it x bar. I mean, the symbol is this x with a bar over it. And the way that you say that, you know, in spoken terms, if you're talking to someone, would be x bar. A lot of times in research papers, you're going to see this as like an italicized M as well. So like when I'm writing a research paper, instead of putting X bar or something like that, I'll just put M equals blah. And when you're looking at a population statistic, though, it's going to be mu, which is this funky Greek looking letter. Well, it's a funky looking Greek letter, rather, right here. Kind of looks like a U with like a goatee, I guess. I don't know. Or a little bit like a sick M. So that's a mu. Sometimes you'll see it as mu sub x right here. And that just means the mean of all of the x values. It's usually mu. You're probably never going to see mu sub x. And then to say it, you just say mu, mu. Could also be MEW. I don't care how you spell it. It's pronounced mu. When we're looking at mode, median, there's not a difference. There's not a difference from sample to population. It's always the median. Sometimes abbreviated as MD, and then sometimes this like X with a tilde over top, that's kind of rarely used. People usually just say the median, whether it's sample or population. Same with mode. It's either mode or MO. Usually it's just mode. We use it so infrequently that we'll just say median or mode. If it was in a paper or something, people might be confused if they saw MD and MO. I know I would, because I'm used to just seeing median and mode. But the mean, the numbers for the mean, or the symbols for the mean, again, that's the most commonly used statistic, so we're used to seeing those kinds of things. X bar, mu, italicized large capital M. Anything like that. So really quickly, I want to tell you about the history of central tendency. This is very, very quick. I think it's awesome. So the first recorded use of central tendency was during the Peloponnesian Wars in Greece. And so what you got going on here, do I have this? Yeah, so this is the city of Plataea, which is being sieged by the Spartan armies. So the Spartan armies put up the siege wall right here. They surrounded the city. And they're just like, cutting off supplies, waiting for Plataea to give up and just stop, being a part of this war. They wanted to take over Plataea. Plataea was allies with Athens, who was at war with Sparta at this time. Anyway, that's not really the important part of the story. It is kind of exciting. You never knew that math was going to be so historical, right? So I was going to say cool, but I guess that's subjective. You might think that both math and history suck. Hopefully not. So what happened was, how tall is this wall? So some people are going to make a run for it. They want to make a run for the wall after the Spartans have gotten kind of complacent. They're not like looking at Plataea all the time to see where the people are who might be trying to make a run for it. They also don't think that anybody's going to try to make a run for it and go over the siege wall. So some people want to, some Plataea citizens, there's also some people from Athens there. What they want to do is make a run for it, get over the wall, and then go to Athens to say, yo, there's a siege wall around the city, can you come help? What they need to know is how tall is this wall, because what they're going to do is they're going to construct some ladders to take with them. They don't want to construct a ladder that's too tall, because that's going to be harder to run with. So they want it to be exactly the right height, so they don't have to do more work than is necessary. So they're going to construct a ladder. So to figure out how tall these walls are, what they did was they counted the blocks in them. the number of blocks tall. And it wasn't quite the same because they're not making blocks that are, like a like 8-inch blocks like we have now, like cinder blocks. They don't have 8-inch tall cinder blocks. So they're finding stones in some cases, or sometimes bricks that have been made, but they're not as uniform as we have in modern times. So they're counting how many are in all these different spots where they can actually see them, because a lot of the wall has been painted, so this isn't a tactic that you can use. But they didn't paint all of the areas on the inside. So they take a count of a whole bunch of different places. Then they find the average of the count, and they kind of estimate how tall these blocks are. They've got blocks in their city as well, so they estimate about how tall they are. They make some ladders that are exactly the size of the average height that they've computed by the number of bricks in the wall, and they actually do make a run for it. They get to Athens, and I think the Athenians come and save the day. See, I'm actually not... Yeah, I'm pretty sure they do. I think the Plataeans got out without starving or giving up. And this is recorded by Thucydides. This is from like 427 BC. This is amazing, right? This is 2,500 years ago. One of the reasons that people from Athens might think to use this is this dude here. This is Pythagoras. Pythagoras is really cool because he's a huge mathematician. The other thing that he's really known for is, if you look at the students that he's teaching here, there's a lot of female students. Most of Greek society was really pushing just men to get an education, which is crazy because their god of knowledge is actually a goddess of knowledge, who's Athena. Their whole city is named after this. But anyway, mostly it's just males that got an education, but Pythagoras was really trying to push these ideas forward of like, let's educate everybody because then society's better off. People didn't totally dig that, and he ended up having to go to Egypt to escape being killed. And then he started a cult. But anyway, he's pretty awesome. From there, we also go into code breaking. How awesome is this? This is Al-Kindi. He was around in, I believe, the 600s, AD, not BC. So this is a significant jump forward from Pythagoras' time. But what was really interesting about this is he was using statistics and central tendency to break codes for his military. The thing is, what's really cool about Al-Kindi is he's not just a mathematician and a code breaker. He's also a musician and a poet and all sorts of things. Like a real big brain kind of guy, right? So what he looks at is a whole bunch of different texts, a whole bunch of different writings. There we go. This is Shakespeare on the left and Stephen King on the right. Two different passages. And what he did was he counted up the number of different letters that occur and how often they occur. What proportion of the text is made up of that letter. And so you can see that in the Shakespeare quote here, there's about 8% of the text is E's, 10% of the text is T's, 0.3% of the text is K's, and 0% is V. In the Stephen King quote, which is a little bit longer, you've got 10% E's, 12% T's, 0.8% K's, and 0.6% V's. And what happens, just so happens that people have done this with a whole bunch of different English texts. We're going to look just at the English language right now. Obviously, Al-Kindi was not studying English. But this is our modern alphabet. This is how often these things occur. So E, 12.5 to 13% of the text is made up of E's. 9% is T's. Blah, blah, blah. K, where's K? Oh, it's here. You can't see it because I didn't make this thing go away. But it's right here. It's about 0.8% of the text would be a K, and a V is right here above it. 0.2 0.8% of the text. 0.9, sorry. 0.9 or 1% of the text is a V. So, very interesting, because it's pretty much the same, right? All these texts, little texts, it doesn't matter how short they are, they come out approximately the same. That was all Kindy's contribution to code breaking. So he would look at these different symbols, or if it was a message where the letters are kind of jumbled around to stand for different things, it doesn't matter if it's symbols or letters or numbers. You look at how often that occurs, and you can then infer that that's probably a certain letter based on how often it occurs in a message. These are the kind of things, if you do cryptograms for puzzles for fun, you totally know about this. This is also the reason why, if you're watching Wheel of Fortune, R, L, S, T, and E are the letters that they give people for free at the end. Those are the most common letters in English. So, how are we going to calculate these measures of central tendency now that you know more than you ever wanted to know about the history of central tendency? Well, you can do it by hand, which is actually, I think it's fun. But again, I also think the history of math is fun. So your results might vary on that one. But I feel like it's kind of like Sudoku, like doing all this stuff by hand. You can also do it in Excel. Doesn't matter how fun it is to do by hand. Excel is a whole lot quicker. So, why not use modern inventions? We can do it with different functions. There's some predefined formulas that we've got for computing all these measures of central tendency. We can also do it with something called the analysis tool pack. Excel is going to be in a second lecture that's coming up, an independent video. Right now, we're just going to focus on doing it by hand. Okay, yeah, that's what I just said. I don't know why I put that slide in there. So we're going to calculate this by hand. Here is your formula for computing the mean. X bar equals, and this is sigma, so the sum of all of the x sub i's over n. So let's kind of break this down into its portions really quickly. X bar, of course, we talked about this already. That's the mean of the values or the scores or whatever you have. Sigma is an operator. It's a mathematical operator that's telling you simply add up everything that follows. And x sub I stands for each individual score. So if x bar means the average test score, let's say, then x sub I means a certain test score. I is an observation number. It's going to be observation 1, 2, 3, etc. So if you have some tests that come in, the first test that comes in, first person that's done, is observation 1. So that test is x sub 1. That's score number 1. The next test that comes in is x sub 2. So x is our variable. The variable here is a test score. And then we've got different observations there. So that's x sub I. And then x bar, again, is the mean test score. And we're dividing it by n. This is the sample size. Okay. So what are you going to do? What you're going to do is you're just going to list the entire set of values in one or more columns, right? One column is probably easiest. These are all of your x sub i's. Then you're going to compute the sum or the total, whatever you want to call it, of all the values. That's the sigma x sub I. Then you're going to divide that total or sum by the number of values that you've just added together, or n. And the answer that you get is the mean. So let's take a look at this a little bit closer. We've got some stores here. They've got different customers coming into these different stores. Let's say that these are VHS tape stores, because why not? And Lanham Park is one of them. Lanham, that's what happens when you plug your pig into Wi-Fi. Turns it into a Lanham. There's like 2 of you that got that joke. It's fine. Don't worry about it. It's not very good. So what we're going to do is we're going to look at our formula here. So we've got the x bar. That shouldn't have an I next to it. I was confused when I put that down. That shouldn't have a little I there. It should just be x bar equals the sum of all of the x sub i's over n. Well, we've only got 3 observations, so it's really easy to put that here, right? So we've got 2,150, that's x sub 1. We've got 1,534, x sub 2. We've got 3,564, that's x sub 3. We have 3 observations. And if we add those together, it's 7,248 over 3, which is 2,416. So these stores at our VHS tape selling store, where I guess, I don't know what we're selling, like only Jurassic Park on VHS. We get on an average of 2,416 customers per year. That's about 2,000 more customers than I would expect for a store that only sells VHS copies of Jurassic Park. So we're doing really well. So that's just a look at the mean. Add it all together, divide by the number of things that you've just added up. Okay, the median, a little bit different. So it is the score, or the number, or the observation, or whatever you want to call it, at which 50% of those scores fall above and 50% of those scores fall below. There's not really a formula for this. You're just going to put the scores in order from highest to lowest, or lowest to highest, it doesn't matter, just in order. And then you're looking for the middle score. Now, this is easy if you have an odd number of values. If you have an odd number of values, so we have 5 here, what you're going to do is, what is 5 divided by 2? It's 2.5. So then you can round up to the next one, which is 3. The next whole number is 3. You're looking for the third value. That should be your middle number, right? So 1, 2, 3, 7. The median here is 7. Yeah, so we're going to come in from both sides. If you don't want to count it, what you can do is just like walk in from the sides. So you just go bloop, and then bloop, and your fingers are going to converge here on 7. This is your median. If you have an even number of values, it's a little bit harder because you're not just going to land on one value. You're going to end up landing on 2 values, right? So we're kind of walking the fingers together, bloop, bloop, and then bloop. The third one where they're going to come together is in this negative space in between 8 and 10. Shoot. What are we going to do? Well, you're going to take the average of the 2 numbers that are in the middle. So you're going to take the average of 8 and 10, which is 18, divide it by 2, which is 9. So your median in this case is 9. You take an average of the middle 2 numbers. So again, if you have an odd number, that's easy to figure out. You've actually got a real middle number. If you have an even number, then you're going to take an average of the middle 2 numbers. If you have an even number, and it's not something that's easy to just kind of like visually look at, like this number here. So like, let's say you have 28 observations instead of 6. What you do is you divide that in half. So 6 and a half is 3. And that means I'm going to be looking for the third value coming from one direction and the third value coming from the other direction, right? So I've got 1, 2, 8. That's the third one. And 21, 20, 10. I'm going to average those together. If you had 28 values, you're looking for the 14th number coming from both directions, right? So then you're going to average those 2 together. Okay, so I was going to give you, yeah, so if you had 27 observations, 27 divided by 2 is 13.5. So you're looking for the 14th observation. That should be your middle number, the 14th from either side. Doesn't matter. You're going to end on the same number no matter what. So that's your median. Okay, if you end up finding the median and you are adding together more than 2 things, you're doing it wrong. You should only ever add together 2 numbers if you have an even number of observations. If you have an odd number of observations, you shouldn't be finding an average at all. You should be landing on one single number. Okay, so let's put this into practice. The mode is the most frequently occurring score. So let's say that we take a sample of all sorts of people at a like a city hall discussion, right? We've got 90 Democrats, 70 Republicans, and 140 independents. Well, there are the most independents, and so that's the mode, is independence. You can also have these kind of interesting things where there are two numbers that occur the same number of times. And that's called a bimodal distribution. And you can kind of see that here in more than just the two modes, right? Like you see that there's two pretty well-defined peaks. And this is a textbook bimodal distribution. We're not going to deal with those much in this class. Just know that they can happen. Okay, let's do some practice. So, we're going to ask 9 people how many servings of fruits and vegetables they ate yesterday, and these are the responses you get. Some people had 2, 3, 4, 2, 6, 3, 3, 1, 4. You should find the mean, median, and mode. So pause this video and find those numbers. And then when you find them, push play, and then we'll go through it. You can check your work that way. I was going to say I'll wait, but you're pausing me. So probably I'm back already and you've done the work. Welcome back. Okay, let's take a look. Let's do the mean first. So the mean is the average. What we're going to do is we're just going to add together all of those numbers. 2, 3, 4, 2, 6, 3, 3, 1, 4, which is, I didn't put it down. Why did I not put it down? And then divide it by 9, which is 3.1. Sorry, I didn't write out all the steps for you. But if you divide it by 9, which is the number of actual values that you have, it's 3.1. That's not a value that's in the original list. Like we only have whole numbers in that list, no decimals. And that's fine. That's totally normal. An average will likely be a decimal. It just often happens. You shouldn't assume that it's going to be one of the original numbers there. When you're doing like a mode, that's going to be one of your original numbers. When you're doing a median, sometimes it's one of your original numbers, unless you have, again, two values that you have to take the average of. But the mean, the arithmetic mean, likely isn't going to be one of your original numbers in the list. If it is, that's just a coincidence. Okay. So the median is the middle value. So what I have to do for this is rewrite all of these values in order. So instead of that jumble of numbers, because it doesn't matter what order you have numbers in to add them together to find the mean, but it does when you're doing the median. So now we've got 1, 2, 2, 3, 3, 3, 4, 4, 6. There's 9 numbers here, so that means I'm going to be looking for the fifth number. 9 divided by 2 is 4.5, and if I go up to the next whole number, that's 5. So I'm going to be looking for the fifth number. Right, so 1, 2, 3, 4, 5. And we could do it from either side, right? 1, 2, 3, 4, 5. So I landed on 3. My median is 3. Easy. Mode, it's the number that is repeated more often than any other number. And you can see that here we've got 1, 1, 2 2s, 3 3s, 2 4s, and 1 6. And so then 3, with 3 observations of the same thing, is going to be the mode. 3 is our mode. And this is everything that we found. The mean is 3.1. The median is 3. The mode is 3. Well, what does this mean? This means that, yeah, this is a pretty normal distribution because the mean and the median are the same value. So we can assume that it's pretty normal. And that's what we like. Great. Let's talk about outliers really quickly. We're going to use the same data set. I'm getting ahead of myself. So an outlier is any observation that's extremely different from the others. Here's some pictures of what's going on. We've got all of these dots that are together, kind of riding up this line right here. Really nice, orderly kind of thing. And you've got this jerk over here. He's kind of screwing it up for everybody, right? what is this guy's problem? Well, he's an outlier. That's just what they do. And again, it doesn't have to be like things are in a line necessarily. These points are all pretty clustered together pretty well, except for this one. That's another outlier. So we've got, outliers. Any observation that is extremely different from the others. There's a few different things that can bring about an outlier. Sometimes they happen. Sometimes it's actual real data. You just do have outliers. Think about IQ. IQ is normed to 100, which means the average IQ is 100. The standard deviation is 10, which means you can expect, within one standard deviation, you've got quite a few people between 90 and 100 with IQs between 90 and 110. And most of your population is going to have IQs between 70 and 130. However, every once in a while, you have like a Albert Einstein or something who's got like 147 or something like that, right? And if you happened to have, let's say you're an elementary school teacher, and you have an Albert Einstein in your class, most of those kids are going to average around 100, and then you've got Albert Einstein, and he's 147. Sometimes it's real. That's an outlier, but it's real data. Sometimes it's an error in your methodology, like you didn't do something right. I'm trying to think of, there was a survey that I was trying to take recently from a company, and I wanted to set a 0. I know what it was. It was not a survey. I was ordering Chinese food online, and I was trying to get rid of the egg rolls that I was ordering because I decided to get crab rangoon. So I put in a 0, and it's like, hey, you can't, that number is not valid. And so it, for some reason, changed it to 99 orders of egg rolls. I don't know why. That would have been an error in the measurement. I do not want 99 egg rolls. I only want 1 or 0. And so that would be the outlier. If you're looking at how many egg rolls does a person order usually, and then they think that Dr. Patton's over here ordering 99 egg rolls. I mean, look, I love egg rolls. I would probably eat 99 egg rolls in a day if it didn't kill me. But it's also really expensive, so I wouldn't do that. Anyway, that's an outlier. Let's take a look at this in practice. So we have 10 people now that we're asking how many servings of fruits and vegetables they ate yesterday, and we get the following responses. It's the same group of people that we asked when there were 9, and then here's your vegan friend, and they had 15 servings of vegetables yesterday. And so things get a little funky. So what happens to the scores? That one extreme score is going to change the mean. It actually doesn't change the median or the mode. So let's take a look at that in this line here. The number that occurs most often, well, 15 only occurs once. 3 is still the one that occurs most often with 3 observations. So 3 is still the mode. 3 is also still the middle number. If we jump back, if we tack on a 15 right here, then we've got 10 observations. So we're counting in 5 from either side instead of just the 5th number. So we're going to go 1, 2, 3, 4, 5. And 1 over here, which is 15. 2, 3, 4, 5. So we've landed on 3 for both of our numbers. Then we're going to average those together. Well, 3 plus 3 is 6 divided by 2 is 3. If it's the same number, you don't have to go through that step. So your mode is, or your median is 3. And the mode is 3. Still the same number. But the average is changing because we're adding in, oh, I'm going backwards. Sorry about that. The average is changing because we're adding in that 15. That's going to change quite a bit. In fact, it's going to blow it up to 4.3. So we're going to go 4.3, 3, and 3. The median and the mode haven't changed, but the mean has changed a decent amount. So what does this mean? That means that the mean, is sensitive to outliers. Outliers can pull the mean in one direction or the other. And that's actually why when we talk about income, average income, we talk about the central tendency of income, a lot of times we use the median household income. You hear that a lot if you listen to like economics podcasts and things like that. That's because if you took the mean income, it would be heavily skewed to show that we're all bringing home a lot more money than we actually are. Why is that? Jeff Bezos makes $1 million or billion or some ridiculous number of dollars per year. So you take all of the people that work at McDonald's who make $30,000 a year and the Jeff Bezos, and you do the average, and because that is such an outlier, it makes it look like everybody that works at McDonald's and Jeff Bezos all bring home about $100,000 a year. Not true, right? Obviously, this is not right. So when we talk about statistics like that are heavily skewed, we use the median. The median income would be much more representative of all those people that work at McDonald's and not Jeff Bezos. And then, so that's my second point there. The median is robust to outliers. The median cares about how many cases, not the values of those cases. So extreme scores just aren't going to influence it. And there you go. The mean is sensitive. The median is not. Let's go back over what we've talked about over this last 30 minutes. The central tendency describes the center point of a distribution of the data set. There's 3 ways you can do this: the mean, median, and the mode. The mean is the most popular measure, but it, again, is sensitive to outliers. The median, however, is robust to outliers. If you have a normally distributed data set, you can use the mean. And all of our statistical tests use the mean. If you don't have a normally distributed data set, there are corrections that we can take with our tests and apply those. There are some tests where you can use the median. This is like super advanced stuff. You're going to only be using the mean. But that is how we, in the advanced realms of data science and stats, deal with non-normally distributed data. A capital N is the population size, and also a mu is the population mean. A little n is the sample size, and x bar is the sample mean. You see x bar in our formula here for computing the mean, which is x bar equals sigma x sub I. That's where the I should have been that I put in the other place. I found it. So it should be x bar equals sigma x sub I over little n. The x is each individual score in the sample. X sub I is each individual score in the sample. And sigma means to sum all those things up. Take the average, take the sum, the total of all of those observations. Okay. So one important thing to note is that no matter how fancy you get with your stats techniques, you can do a t-test, an ANOVA, a z-score, a multi-level model, a structural equation model, tree-fitting algorithms, all sorts of crazy things. It doesn't actually matter. You're usually just going to start by simply describing what is there. People always want to know what the average is. So when you're writing these things up for publication, you always say what the average is of, let's say, men got this score on number of anger outbursts during go-kart racing, and women got this number of angry outbursts during go-kart racing. You give the mean for all these different people, and then you show that those are statistically different or statistically the same, whatever. But we always kind of want to know what the mean is. So it's really important to start by describing this distribution so people can kind of visualize that before you do your statistical test. Okay, here are some additional resources for what we've talked about. You've got these slides, so you can click on any of these links. You can also type them in if you want to pause. And eventually I'll put these links in the comments section too. Not the comments, but you know, the description of the video. So you should be good. And next we're going to talk about how to do all this in Excel. It's a lot quicker than doing it by hand, but maybe not as fun. Okay, I'll see you in that next video.